Welcome back to this video series on how to do quantum mechanics using programming. In this video, we're going to continue to look at the properties of the wave function through the lens of programming and Python. And as always, if you like this video and would like to share it with so more people can see it, then please like, share, subscribe, and comment in the comment section. So last video, I gave you the exercise to do some numerical integration. Just going to create a Colab environment here. And I ask you to integrate these three integrals, and that's what we're going to start with. So I'm just going to name this 3. So let's just go back to our previous file here, and we're going to just pick up our function. So which one do we need? So we need to create the system, and we need to have this wave function that we're going to be integrating. Right, so first we're going to integrate this field psi. Now, the way to do integration there are several ways to do numerical integration. There are methods in NumPy, for instance, which use a trapezoidal method or Simpson's method, or a lot of different things that you can do. But the very simplest method is just to approximate the integral, which is an analytical object, with its Riemann sum. So the Riemann sum is essentially just this discrete version of the integral, and for a lot of the purposes that we're going to be using in this video series, that is actually going to be enough. So we're getting an error here. Yes, because I haven't imported confit, so I need to do that. So import confit as CF, import numpy as NP. No errors. All right. So now we have our function here, psi, which is just an array of numbers. So, to integrate it, we need to calculate what we have here. So f of x times delta x. So that is simply going to be qm, or qm.psi, that's the function we want to integrate, multiplied by qm.dx. So now we have the thing that is here, and then I want to sum over all the x values from minus 10 to 10. Now, minus 10 to 10 is exactly the limits of my system, which means that this is simply just going to be the sum of all of these things. And I wonder if this works, even though psi is a number. Yeah, and it actually works. So we get that the integral is a complex number, and the real part is 0.819, and the complex or the imaginary part is 0.081i. So that's the first exercise. Now for the second exercise, we are going to have to square this integral first. So if I take this function, and now instead of doing qm.psi, I'm going to do the absolute value of qm.psi and then square it and then multiply by dx. Then I get a real number, it says, which is 1.00000000007. So essentially, it's 1. And that's not a coincidence, and we'll get back to that in a minute. But lastly, the third exercise was to calculate the integral from minus 2 to 2. And then the question is, how do you do that numerically? Well, we have our array of x numbers going from minus 10 to 10. If I write a condition on this x value, like qm.x smaller than 2, then I get the value. Then I get a Boolean array, so an array of bool values telling me which of these points is this condition satisfied for. So It's true for -10, and it's true for all the x values up to this point. And after this point, it's no longer true, probably because the x value from here is larger than 2. And the reason that we have this is that actually, if I name this, like, if I name this interval, this array here, then I can actually write qm.psi of interval. And what it does then is that it picks out from this complex array only the values for which this is the case. So it doesn't look like it here, but there are actually fewer values in this array than there was before, because now it's only the values where qm is smaller than 2. Now, of course, what we're really interested in is not just the values where qm is smaller than 2, but we want the values where qm is larger than -2 and smaller than -2. And the way to do that in Confit is simply to multiply qm.x larger than -2 with qm.x, smaller than 2. So what I get then is an array which tells me like, oh, this is false for all the x values up until this point where it's true, and then it turns false again when x is larger. And now if I name this thing, this array interval, just to remind you, interval is just this array of false true values, then I can write qm.psi of interval, and now I only get the values of psi which are between -2 and 2. And so therefore I can do the integral the same way I did before by writing sum of this thing multiplied by qm.dx. And what I do get, and I was also going to do, the squared, right? So I'm going to do the absolute value of this thing here, squared multiplied by dx, and the value I get is 0.95159, etc. So this is how to do numerical integration the very simplest way. So what we're going to do in this video is that we're going to have a look at what we call the Born rule. So even though Schrödinger had derived his in the 1920s derived his Schrödinger equation and gotten to this wave function, people were still wondering about like, okay, what is this wave function? And then Born came with this famous Born rule, which sort of gave an answer to this question, where he said that like the wave function is a kind of probability density, where the integral from a to b of the square of the wave function is the probability of measuring this particle between these two points. And in fact, this notion that quantum mechanics gave probabilities of measuring something is another break with classical physics, because now the theory in itself is indeterministic, meaning we don't know what the outcome of some measurement will be. We only know what the probability is. But it does force a condition on our wave function that the integral from -infinity to infinity should be 1, because essentially if this is the probability of measuring the particle between A and B, then if we look at what is the probability of measuring the particle somewhere between -infinity and infinity, this should most definitely be 1. And so the reason that we often work with Gaussians, and the reason that we're going to be working with Gaussians, is that they're kind of very nice localized functions. And if we write them properly, they will in fact integrate to 1. So this is the definition of a Gaussian function in one dimension. So it's g of x 1 over the square root of 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared. It has two parameters, which is sigma and mu. And sigma is going to be denoting the width of the wave function. So sigma is, if we draw like a width of 2 sigma here, is going to capture like 70% of the Gaussian function, and mu is the center of the Gaussian wave function. So those are 2 parameters. And as I said, this function has the property, when it's properly normalized like this, it has the property that the integral from minus infinity to infinity of this function is 1. Now, we want a wave function which, when squared and integrated from over all of x, gives 1, which means that we define psi of x as the square root of this g of x function. And that is actually what you get when you plot, if I do qm.plot field, plot complex field, qm.psi, this is actually the shape. Oh yeah, I forgot to write fig and x again. This is actually the shape that you get from this wave function. This is actually what's happening inside this function here. Configure initial Gaussian function is setting the psi to be that have that profile. So then we have like a candidate for a wave function. Now we're going to play around with it, giving it velocity, etc. But there's a different type of wave function that's also very interesting to play around with, and that is something called a plane wave. And the plane wave function, it's not really a wave function because it's not possible to integrate it from minus infinity to infinity and get a number, but it's a very useful construct in thinking about quantum mechanics and modifying the Gaussian wave function. So if we look at this function, e to the I kx for some number k, let's just assume like k is 1 for the time being. Now, let's say that for some value of x, the kx is going to be equal to this angle here. Now, e to the I kx, the amplitude of this number is always 1. And the thing that multiplies I in the exponent is actually the phase. So this number here is actually located here in the complex plane with a phase that kx. And you can see that in this case, the phase is approximately 2 pi over 3, which is why I have calculated it, which is why I've colored it green. And to be honest, I don't remember why I wrote this now. I think I meant just to explicitly say something about this being approximately 0.66 pi and this being 0.33 pi. So here we have here is the value of this function. Now, if I increase x, and k is the same, meaning that we're moving to the right in space so that kx increases, then what's going to change is exactly the phase, right? So when I increase x, I increase the phase, but the amplitude is still 1. And so in this case, I've colored the phase to be, well, it shouldn't be blue actually. It should be more like teal, but I wonder if I was missing teal as a color. Yeah, so this was the color that I had. But at this point, the phase is like approximately almost pi. So it's like this teal value here. And so if I plot this function e to the ikx in the way that we have been plotting our wave functions, since the amplitude is always 1, it's going to give us this one line here. So amplitude is always 1, but as we increase x, the color is going to be changing. So from phase 0 to pi and back to 0, and then it's going to go like change these colors all the time. And at some point, the phase is going to come back around and reach the same angle 0 again, at which point the value of the phase is going to be 0, and it's going to be colored red again. So you see that this plane wave, when I plot it in this way, it's going to have this periodicity where it's red and then goes through all the colors and then back to red again. And when does that happen? Well, it happens when the argument of this, or the phase of this function here, has changed with a factor of 2 pi. In other words, when k times the change in x position is 2 pi. And so since the phase is changing, this is what's typically called a phase gradient. So because it's gradient, it's changing, and it's in the phase. So it's a phase gradient. So if you hear that word, now you know what it means. And obviously, this distance, or the distance from here to here when it repeats, that's what we call the wavelength of the plane wave. So the wavelength is defined as 2 pi divided by this k number, which is called the wave number. Now, de Broglie, he suggested that actually the momentum of a particle is given by h divided by this wave number, which means that if I insert the definition of the wave number as 2 pi over k, then I get that the momentum is supposed to be h bar times the k, where h bar is Planck's constant divided by 2 pi. So we have sort of two kind of functions to play with. We have the Gaussian function, which is creating something that's sort of localized in space, and then we have these plane waves, which indicate a state of the system which has a defined momentum given by h bar times k. So let's have a look at the programming. What we're going to do now is we're going to just have a look at this Gaussian wave function, and then we're going to be having a look at the plane waves, and then we're going to combine them in order to give the state that we're working with a velocity. And if you feel comfortable, then I suggest that you pause the video and you try to solve, and you try to do all the things that you expect me to be doing first, and then see if I end up doing the same thing as you did. All right, so we've already had a look at this Gaussian function, right? But now let's do it properly. So we get qm.psi is here. If I take the absolute value of that and I plot this, yeah. Also, I'm going to do another thing, which is that in all the previous cases, when I did like fig and then x equaled to this, and then I plotted fid, what I can do to simplify this is essentially just state that I only want the first return from this function, which will only give me fig, and then it's going to display directly. So if I just add 0 after this, it's going to display my function directly. And as we can see, the absolute value of qm.psi is this Gaussian function with a width and a mean, which is surprisingly not exactly at 0. I don't know exactly why that is the case, but that's what happens. Now, I can create a different kind of function. So if I do conf initial state condition Gaussian, if I set the width to be 2, for instance, instead, and then plot this function, you can see that now it's like more spread out in space. So there is that. Okay, and we also gave it an initial. We don't have to do this now. Now, as we know, when we integrate this function from -10 to 10, we're supposed to get 1. And let's just verify this. Also, previously we did this sort of sum thing in order to integrate the wave function. There's actually a function in comfit which does this for you, which is qm.calc integrate field, and then that takes the field that you want to integrate. So if I only give like apps as an input to this, then it's going to just calculate over the whole of the domain. And as we know, this gave us 1 as we expected. And if I want to integrate over an interval, I have to define my interval as before. So Gemini is suggesting it correctly. So I'm looking at the interval between -2 and 2, and then I need to pass that interval as the second argument of the calc integrate field. And then you can see 0.951, which was exactly the value that we calculated previously. Now, what does this mean? It means, since this is the absolute value of the wave function squared, it means that it's a proper wave function, because when I integrate over the whole domain, I get 1. So the particle is going to be found somewhere. But when I integrate between -2 and 2, so when I integrate this region here, I actually get 0.951. And this means that there is according to the Born rule, there's a 95.1 or 95.2% chance of finding the particle between -2 and 2. So that's the Born rule. So that was the Gaussian. Now let's have a look at the plane wave. So I'm going to define plane wave is equal to, and is I times k times qm dot x. Now, exp is not defined because that comes from the numpy package. K is also not defined because I haven't defined it yet. So I'm just going to write k equal to 1 to begin with. And then I have defined an array which contains the plane wave. So if I print it, it's just an array of complex numbers. But we can plot it, as always. It's a complex field, so I need to use complex field, plane wave, and then I only want the fig object, so I add the 0. Then we can see, exactly as we expected, that the amplitude is always 1. And as we increase in the x direction, the phase increases and then goes to pi, and then goes to minus pi, and then goes back to 1. And then we see that the wavelength of this function is 2 pi. So from 0 to 6.28, which is 2 pi. So that's the plane wave. If I take this and add it here, if I double the wave number, essentially it's going to make this part of the plane wave increase twice as fast, which means that we're going to get like this red more close together, and that is exactly what we see. So now we have sort of changed this the periodicity here. And if we go back to the Broglie relation, we see that the momentum of this plane wave is given by h bar times k, which means that this wave function here, which has k, which is twice as large as this one, according to the Broglie, actually carries twice the momentum of this phase. And if the mass is the same, it means that the velocity of this wave packet is twice as big as the velocity of this package, this wave function here. And actually, in Comfit, as we'll see in a few videos later, we're actually working with dimensionless units, which means that we're setting h bar to 1, we're setting c to 1, we're setting m to 1, and so therefore all of these numbers here are actually correct. No, what I'm trying to say is this is actually the velocity. So this one will say that this one has a velocity of 2, and this one has a velocity of 1. And so if I now start with my field here, so if I create this initial Gaussian with the width of 1, if I now plot the complex field, qm.psi of 0, you can see that it has this Gaussian shape, and then it's always, the phase is just 0. Now, if I take this plane wave here, like this, and then I set k to 1, I have this plane wave function here. Now, if I multiply this qm.psi field with the plane wave, I get this, which is essentially a wave function it's a Gaussian, so the particle is localized in this region, and it's a wave function which has an expectation value for the momentum to be 1, or the velocity to be 1. And in fact, this is exactly what we this is exactly so this is exactly the function that we get if we set the initial velocity of the function to be 1. Well, not exactly. Why not? Oh yeah, okay. Of course, I need to do either or, because now I multiplied it with it twice. Yeah, so it's either right. So here, what I'm doing here is I'm creating this initial Gaussian wave function with velocity 0. I'm multiplying with the plane wave, which has a wave number of 1, and then I'm multiplying those together. I'm plotting it, and that gives me exactly the same result as if I set the initial velocity of the initial Gaussian as 1. That was my point. So that's a Gaussian, that's a plane wave. And essentially what we're going to be seeing later on as we get into when we get the Schrodinger equation, is that we're going to see that if we give this initial wave function this initial velocity, then the whole wave function is going to move to the right. So there's that. So for the next video, my exercise for you to try to do is to try to create a Python function that takes this function psi, or an array psi as an input, and returns the derivative of psi as an output of that function. And I will see you in the next video.